Welcome to the Deep Dive, the show where we give you a shortcut to being truly well informed. Sometimes you look at a subject, especially something as complex as organic chemistry, and it just seems like this impenetrable wall of information. But what if I told you that underneath all that complexity, there are often elegant, surprising solutions and core players that, once you understand them, make everything else just sort of click? Okay, let's unpack this. Today, we're taking a deep dive into a really foundational and frankly pretty electrifying part of organic chemistry. We're talking about reactions involving what we call reactive intermediates. Mm. Our focus will be primarily on carbocations and carbenes, these high-energy, really fleeting chemical species that drive some of the most intricate molecular transformations you can imagine. Our mission for you, our listener, is simple. Walk away from this deep dive with a crystal clear understanding of these short-lived chemical powerhouses. We're going to cover their fundamental nature, how they manage to form bonds even though they barely exist, the unique reactions they drive, and crucially, how brilliant chemists actually harness their incredible power for, sophisticated synthesis. It's all about getting to those aha moments without feeling totally swamped by information.
And to achieve that, our deep dive today draws directly from Advanced Organic Chemistry Part B Reactions and Synthesis 5th edition, which is, a truly authoritative source in the field. This particular chapter zeroes in on what are called electron-deficient reactive intermediates. That includes carbocations and carbenes. Both of these have a carbon atom with only 6 valence electrons, which makes them, by definition, highly electrophilic. They're basically electron-hungry. Now, the chapter also touches on carbon-centered radicals. They involve 7 valence electrons, react differently. But our primary focus today, reflecting the chapter's emphasis, will be on these electron-hungry carbocations and carbenes. What's fascinating here is, a common defining feature across all these intermediates, carbocations and carbenes, is they're inherently high energy, much higher energy compared to molecules with completely filled valence shells. This high energy means their lifetimes are usually, and I mean dramatically short, we're talking fractions of a second. But despite their fleeting nature, the bond formation steps involving them often occur with exceptionally low activation energies. This is particularly true for addition reactions, especially when they react with alkenes or other systems with pi bonds. These reactions are incredibly thermodynamically favorable because they typically replace a weaker pi bond with a stronger sigma bond. So the whole process is highly exothermic. It releases a lot of energy.
Okay, so that's interesting. They're unstable, but they react fast.
Exactly. Fast and energetically downhill.
And here's where it gets really interesting, I think. Because of these incredibly low energy barriers to forming bonds, the precise three-dimensional shape or conformation of the reactant molecule often plays an absolutely decisive role. It dictates the outcome. Carbocations and carbenes frequently undergo very efficient intramolecular reactions happening within the same molecule. And this efficiency is critically dependent on the reacting centers being, really close together, allowing for rapid interaction. Think of it like a molecular handshake that has to happen immediately because these intermediates are just so impatient. Conversely, reactions that would require them to twist into unfavorable shapes, those are pretty rare, or at least highly disfavored.
That's precisely right. For anyone involved in designing new synthetic routes or, analyzing how reactions actually work in organic chemistry, paying exceptionally close attention to these conformational factors is paramount. This isn't just some academic theory. It directly impacts the specific products you get. It determines the success or failure of a synthetic route. It's all about understanding the subtle dance of atoms and electrons and how a molecule's shape really dictates its destiny.
Right. So let's shift our focus now specifically to carbocations. Remind us again, what are they?
Carbocations are carbon atoms that carry a positive charge. They're missing electrons, so they're very eager to find some. For this deep dive, we're going to concentrate on carbocation reactions that specifically modify the carbon skeleton. That means they literally change the molecular framework. This includes forming new carbon-carbon bonds, some really fascinating rearrangements that can dramatically alter the structure, and even fragmentation reactions where carbon-carbon bonds are intentionally broken apart.
Okay, carbon bond formation first. How does that work with these carbocations?
At its core, it involves what we call electrophilic attack. Imagine a carbocation, which is electron deficient, seeking out an electron-rich double bond, like you find in an alkene. The basic idea is pretty simple. A positively charged carbon attacks a carbon-carbon double bond. You form a new carbon-carbon bond, but you also create a new carbocation at the end of the chain. This process happens readily It releases energy, so it's thermodynamically favorable.
Ah, but there's the catch. The product is also a carbocation. I can see where this leads.
Exactly. That's the serious challenge for synthetic application. That new carbocation can just react further, adding to another alkene molecule and another and another.
Leading to polymerization, basically making plastic instead of your specific target molecule.
Right. And on top of that, there's always the possibility of unwanted rearrangements within that newly formed carbocation. So you end up with a messy mixture of products, not the single desired molecule.
So for these reactions to be actually useful in synthesis, chemists need really precise control of the reactivity of that new carbocation. They need like a way to stop the chain reaction, a suitable termination step.
That's where some clever strategies come in. One highly effective approach uses specialized molecules called alkenyl and allylic silanes or stananes. These have silicon or tin groups attached near the double bond. The beauty here is that after the initial electrophilic attack by the carbocation, that silyl or stanyl group is cleanly eliminated. It just pops off. And that leads to the rapid formation of a stable alkene product. That provides the crucial termination step, preventing that unwanted polymerization.
Ah, so it attacks, and then the silicon or tin leaves, shutting down the reactivity. Clever.
And there's a dual advantage. These silyl and stanyl substituted alkenes are actually more nucleophilic than simple alkenes, meaning they're even more attractive to the carbocation in the first place. Plus, it ensures the starting materials are more reactive than the products, which favors a clean, high-yielding reaction. This elegant concept extends beautifully to other silicon-containing regions, things like silly-enol ethers and silly-ketene acetyls. Again, a carbocation attacks, and then a distillation step occurs, yielding a stable alpha-substituted carbonyl compound, a ketone or ester, with a new group next to the CO. For instance, this method provides a really valuable way to introduce complex alkyl groups, even bulky tertiary ones, right next to a carbonyl group. Which you mentioned is tricky with other methods. Very tricky with traditional base-catalyzed methods, yeah. They tend to cause other side reactions. So, in one example from the book, reacting a silly-enol ether with the specific tertiary chloride, using a Lewis acid catalyst like Tioxyl-4, effectively gave the alpha-substituted carbonyl compound in good yield, like 62%. Similar reactions work with other types of starting materials and various catalysts, showing how versatile this is. We even see alkylations promoted by allylications using lithium perchlorate, achieving really impressive yields, sometimes over 90%.
Okay, so these reactions clearly work. They demonstrate the feasibility of intermolecular carbocation alkylations, but it sounds like they require very specific setups.
They do. It's important to summarize that despite the feasibility, the requirements for achieving good yields are quite stringent. You need the right catalyst, the right temperature, the right silane or stanyl group.
Which limits their broader application in general organic synthesis. They're powerful tools, but maybe niche tools.
Exactly. Powerful, but for very specific, well-controlled scenarios.
Okay, but you mentioned one area where carbocation alkylation is really synthetically useful. Polyene cyclization.
Yes. Now, here's where it gets really interesting. Arguably, the most synthetically useful of the carbocation alkylation reactions is the cyclization of polyenes. Imagine a long, flexible molecule with multiple double bonds strategically placed along its chain, like a string of pearls, but the pearls are double bonds.
Okay, got it.
Under the right conditions, these polyenes can undergo a cascade, a whole sequence of successive bond-forming steps. They effectively stitch themselves up into complex polycyclic compounds.
So one reaction triggers the next, which triggers the next, forming rings as it goes.
Precisely. This process, polyene cyclization, has proven to be an incredibly effective way of constructing molecules containing 5, or more commonly, 6-membered rings. And these ring structures are incredibly common in natural products like steroids and terpenes. The mechanism involves an initial electrophilic attack, maybe from protonating an alcohol or opening an epoxide, which then triggers this chain of cyclization steps. It's crucial that the double bonds involved are positioned just right to allow these successive attacks to happen smoothly. For example, in the text, an allylic alcohol is quantitatively converted, meaning almost 100% yield, into a specific bicyclic product when treated with just formic acid.
Wow, just formic acid.
Yep. The reaction is initiated by protonation and loss of water, forming the initial carbocation. This then cyclizes efficiently, and the process is finally terminated when a nucleophile, maybe the formate from the acid, captures the newly formed carbocation, stabilizing the molecule. And what's even more remarkable is that longer polyenes aren't limited to just 2 rings. They can continue this cascade, cyclizing to form even more complex tricyclic or tetracyclic systems in a single elegant step.
That sounds incredibly efficient for building complex molecules.
It is. And a truly remarkable aspect of these cyclizations is their exceptionally high stereoselectivity. The precise three-dimensional outcome is largely determined by the initial conformation, the shape of the reactant. For instance, in complex fused ring systems like decalins, two fused six-membered rings, the exact stereochemistry of the ring junctures, how the rings are joined, can often be accurately predicted. We assume the cyclization occurs through conformations that resemble chair cyclohexane rings and that each new bond forms via an anti-attack at the double bonds. This leads to predictable outcomes whether the ring fusions will be trans or cis.
So the starting shape dictates the final 3D structure. That's amazing control.
Well, it really is. Now, to make these synthetically useful, initiating that cationic site that kicks off the cyclization needs to happen under mild conditions. Formic acid, as we saw, or maybe formic acid with stannate chloride, are often effective for allelic alcohols. Acetyls are another clever way they generate potent electrophiles called oxonium ions in acid. Another major route is acid-catalyzed epoxide ring opening, often using Lewis acids like BF3 or SNCl4. Even mercury ions can trigger these cyclizations, sometimes with neighboring groups helping out.
Okay, but you mentioned carbocations can lead to mixtures. Does that happen here too? Capture by solvent, deprotonation, that sort of thing?
It can, yes. That's a common issue. The intermediate formed is a carbocation, so it can react in different ways, leading to mixtures.
But chemists have found ways around this. You mentioned silly groups earlier.
Yes, exactly. Designing reactants with structural features that specifically facilitate the transformation of that final carbocation into a single, stable product is key. And allylic silanes are incredibly useful here. They provide a very favorable termination step through desalination end. The silicon group leaves cleanly, forming a stable double bond. It's like a built-in off switch. And this isn't just about controlling the product. Incorporating silicon groups can dramatically improve the efficiency too. There's a stark contrast in the book. Cyclization of a polyene without a silicon group gave a mess at least 17 different products.
Wow.
But its allylic silane counterpart gave a remarkable 79% yield of a very clean 1.1 mixture of just two stereoisomers. That's a huge difference.
So the silly group acts like a reactivity booster and a clean exit strategy.
Precisely. It enhances reactivity and selectivity. Now, efficiency is also affected by subtle electronic and geometric factors, what we call stereoelectronic factors. Studies show a big difference between Z and E isomers of the same compound. Only the Z isomer allows optimal electronic alignment for stabilization during the reaction, giving much higher yields. The E isomer lacks this perfect alignment and gives much less product. These effects suggest a considerable concerted character, meaning bonds break and form almost simultaneously. Interestingly, if the cyclization terminates with an alkyne instead of an alkene, you form vinylcations, which react with water to give ketones, another tool in the box. And what's really exciting now is the development of methods using chiral acetyl groups. These can induce enantioselective cyclization, giving products with very high enantiomeric excess, mostly one mirror image form.
This sounds incredibly powerful, almost like how nature builds things. You mentioned steroids.
You're absolutely right. Polyene cyclizations are hugely valuable for synthesizing polycyclic natural products like terpenes and steroids. These lab syntheses really mimic the amazing processes in living organisms. The most dramatic biochemical example is the conversion of squalene oxide into lanosterol, a complex steroid. In biology, enzymes act like molecular sculptors, precisely controlling the substrate's conformation, directing the cationic cyclization, and subsequent rearrangements with absolute stereochemical control. It's molecular origami at its finest.
Nature had it figured out first.
Pretty much, and chemists have learned a lot by studying it. Looking at examples in the literature, we see simple protonation leading to six-membered rings, complex cascades forming tricyclic systems. We see alkynes terminating cascades to make ketones and steroidal frameworks, epoxides initiating reactions, and, as we discussed, silicon ethers terminating cyclizations to give ketones with great efficiency. It really shows the versatility and precision chemists can achieve.
Okay, let's shift gears slightly to another type of reaction involving alkenes, inpretherin, and carbonyl reactions. What are these?
Right, the ene reaction. Imagine an electrophile, we call it an enophile, adding to an alkene. But it's not just addition. At the same time, an allylic hydrogen, a hydrogen on the carbon next to the double bond, gets transferred to the enophile.
So addition and hydrogen transfer happening together.
Exactly. The whole process is the ene reaction. Now, if that enophile happens to be a carbonyl group, a CO, we call it a carbonyl ene reaction. Sometimes it's also called the Prinz reaction. These are incredibly useful because they consistently yield delta gamma unsaturated alcohols. So you form a new CC bond, and get an alcohol group positioned specifically relative to a new double bond. And the beauty is the concerted mechanism where everything happens in one synchronized step is allowed by fundamental rules, the Woodward-Hoffmann rules specifically. The transition state involves electrons from the alkene, the enophile, and that allylic CH bond all moving together.
Okay, so under normal thermal conditions, what makes these reactions go?
Well, since the enophile is usually the electron seeker, its reactivity increases if it has electron withdrawing groups attached. That makes it even hungrier for the alkene's electrons. Simple alkenes react pretty slowly thermally, but things like acrylate esters or maleic anhydride are much more reactive enophiles. For carbonyls, highly electrophilic esters like glyoxylates work well thermally. And there's good mechanistic evidence supporting this concerted cyclic transition state for thermal interreactions. Stereochemistry studies show the product geometry matches what you'd expect from a concerted process. The reaction isn't very sensitive to solvent or electronic effects, which points away from highly charged intermediates. And crucially, there's a primary kinetic isotope effect, meaning breaking the CH bond is part of the slowest rate-determining step.
Sure.
All signs point to concerted.
But then, here's where it gets really interesting synthetically. You mentioned Lewis acids.
Yes. This is a game changer. The carbonyl-ene reaction is strongly catalyzed by Lewis acids, things like boron trifluoride, BF3, tin tetrachloride, SnCl4. This catalysis is huge because it lets these reactions happen at or even below room temperature, making them much more practical for chemists.
Why do Lewis acids help so much?
It's quite elegant. The Lewis acid coordinates to the oxygen of the carbonyl group. This pulls electron density away, making the carbonyl carbon much more electrophilic, much more attractive to the alkene. This also makes the reaction much more polar, and so it becomes much more sensitive to solvent and substituent effects. Mechanistic analysis suggests these Lewis acid catalyzed versions are basically electrophilic substitutions. While they can still be somewhat concerted, in practice they often seem to proceed via a stepwise mechanism where a carbocation is formed as an intermediate, or at least the transition state is very carbocation-like.
So the Lewis acid changes the mechanism, potentially?
It pushes it towards a more stepwise, polar mechanism, yes. There's good evidence for this. Isotope effects support either a stepwise path or a concerted one, where CC bond formation is way ahead of hydrogen transfer in the transition state. Computational studies also favor a stepwise mechanism with Lewis acid catalysis, explicitly showing carbocation formation.
Okay, but if it's stepwise, does that mess up the stereochemistry we saw in the thermal reactions?
Surprisingly, often not. Despite the potential for a stepwise mechanism, the stereochemical outcome under Lewis acid catalysis frequently remains remarkably consistent with a cyclic transition state model. For example, steric effects, like from a bulky trimethylsilyl group, can still exert strong control, directing the reaction to give mainly one stereoisomer by avoiding clashes in the transition state. Computational studies really help visualize this. They confirm concerted mechanisms for simple thermal interact states. But for catalyzed reactions, the calculations show much more asynchronous transition states. CC bond formation is highly advanced. The alkene part looks almost like an allylic carbocation, even if it's not fully formed.
And these calculated structures actually predict the real-world results.
They do. The calculated transition state geometries perfectly correlate with observed stereoselectivity. For instance, SnCl4 might chelate the reactants in the transition state, forcing an exo arrangement and giving the antiproduct. But LCl3 might not chelate, allowing an endo-transition state and giving the syn product.
So the choice of Lewis acid directly controls the 3D outcome. Incredible.
It really is. And this Lewis acid catalysis has vastly expanded the utility of the carbonyl interaction. Now you can use less reactive aldehydes or activated alkenes like enol ethers with various metal catalysts like ytterbium or scandium triflates. We even see clever tricks like using molecular sieves not just as drying agents, but as proton scavengers to prevent side reactions and boost yields.
Okay, this is already impressive, but I feel another really interesting point coming. Chiral catalysts.
You guessed it. With the development of chiral Lewis acid catalysts, the carbonyl enabling action can now be made enantioselective. This is huge for making specific mirror image molecules, vital for drugs. Some of the most successful catalysts here are titanium bienol complexes and various copper complexes with chiral BOX ligands.
And they work well. High enantioselectivity.
Exceptionally well. We see examples in the literature achieving 95%, 96%, even 98% enantiomeric excess. That's near perfect control over chirality. Mechanistic interpretations suggest the aldehyde coordinates precisely to the chiral metal catalyst, creating a defined pocket. The alkene then approaches from the sterically least hindered direction, leading to the observed high enantioselectivity.
Wow, okay, so that's intermolecular. What about intramolecular interreactions, closing rings?
Yes, most carbonyl reactions used in synthesis are actually intermolecular. The enophile and alkene are tethered together in the same molecule.
Makes sense. Proximity helps.
Exactly. These cyclizations work thermally or with Lewis acids, but Lewis acids are generally preferred for control and efficiency. Stannic chloride, for instance, nicely cyclizes unsaturated aldehydes to cyclic alcohols. And these intramolecular versions offer fantastic stereocontrol, often favoring one geometric isomer heavily. Plus, with chiral ligands, you can get high EE here too. They're also great team players. They combine well with other reactions in tandem sequences. You can have a cyclization followed by trapping with a nucleophile, or even trigger a cascade, like the Mukiyama-Anie sequence used to make complex tetrahydropyran rings found in natural products like leucoscandrolide.
So many applications.
Absolutely. The examples are vast. Thermal reactions forming rings, intermolecular reactions using tricky enophiles, intermolecular cyclizations building complex fused systems with specific stereochemistry. And, of course, the regioselective versions, delivering products with near-perfect chiral purity using catalysts like titanium vinyl or copper p-bike systems. It's a really powerful and versatile toolset.
Okay, let's move on to another way carbocations form CC bonds, reactions with acylium ions. What are those?
Acylium ions are essentially positively charged acyl groups, RCO+. They're potent electrophiles. Alkenes can react with acylaldehydes or acid anhydrides in the presence of a Lewis acid catalyst. This generates the acylium ion, which then attacks the alkene. The typical product is a beta-gamma unsaturated ketone, meaning the double bond ends up 2 carbons away from the ketone group.
And you mentioned these work better with cyclic alkene.
Generally, yes. The mechanism involves the acylium ion attacking the alkene, and then there's often an intramolecular deprotonation step, which kinetically favors forming that beta-gamma enon product.
It sounds a bit like the N reactions again. Intramolecular specific proton removal.
It does share similarities. Both are effective intramolecularly for ring closure. Both seem to involve highly polarized transition states. And both often show strong specificity in proton abstraction, consistent with a cyclic mechanism, even if not strictly concerted in all cases.
Yeah.
Various conditions work. Using Lewis acids like ethyl aluminum dichloride often gives good yields of the beta-gamma enon, maybe with some beta-haloctone byproduct. Zinc chloride is also good, especially for cyclic alkenes. In some cases, like with simple alkenes, the reaction can be very regiospecific, suggesting a concerted path. Highly reactive mixed anhydrides can also be used, sometimes triggering tandem reactions like acylation, followed by intermolecular Friedel-Crafts alkylation to build complex fused rings like tetralones.
So mostly used for ring formation again.
Primarily, yes. Intramolecular examples show efficient cyclizations to form 5 or 6 membered rings, even in complex structures, using various Lewis acids or specialized reagents like polyphosphoric acid, trimethyl ester, PPSE.
Okay, so carbocations form bonds, but they also love to rearrange, right? That sounds potentially messy.
It can be, yes. Carbocations are inherently prone to rearranging into more stable isomers. A less stable carbocation will happily shift an atom or group around to become more stable. The key to making these rearrangements synthetically useful, rather than just a nuisance, is achieving controlled and predictable outcomes.
How do you control something that wants to rearrange?
By careful design. You leverage substituent effects and stereoelectronic factors, the electronic influence of nearby groups, and the 3D geometry. Some of the most reliable rearrangements are those directed by oxygen substituents, which provide remarkably predictable outcomes.
And the classic example is the pinnacle rearrangement.
Exactly. While carbocations can rearrange by shifting hydrogen, alkyl, alkanol, or aryl groups, the pinnacle rearrangement is a prime example of a controlled rearrangement. It specifically involves carbocations that have a hydroxyl H group on an adjacent carbon. This adjacent ACO-H group assists the migration, leading cleanly to the formation of a carbonyl group, CRO. The overall reaction is the acid-catalyzed conversion of a 1,2-diol, 2 OH groups on adjacent carbons, into a ketone or aldehyde.
And the classic example really brings this to life. Converting 2-pentan-3 dimethylbutane 2-piton-3-diol, which is actually called pinacol.
That's right, the namesake.
Into methyl T-butyl ketone called pinacolone. Using acid, good yield. It's a textbook reaction because it's so predictable.
It is. The mechanism starts with acid protonating one OH group, making it a good leaving group, water. Water leaves, forming a carbocation. Then a group, like a methyl group in pinacol itself, from the adjacent carbon migrates over to the carbocation center. This migration is helped along by the remaining OH group, which uses its lone pairs to stabilize the developing positive charge. Which group migrates depends on stereochemistry and migratory aptitude. Generally, groups that can stabilize positive charge well, like vinyl or aryl groups, migrate readily. Computational studies give an order: vinyl cyclopropyl, alkynyl methyl, methyl hydrogen.
And electron-releasing groups on, say, a migrating alkynyl group would make it migrate even faster.
Precisely. This has been cleverly used, for instance, with trimethylsilane substituted groups migrating selectively. There's even an example where a silane reagent first reduces an intermediate and then promotes the pinacol-like rearrangement, leading to a primary alcohol. Exquisite control.
What about controlling which OH group leaves in the first place?
An excellent strategy for that is using glycol monosulfonate esters. You selectively make one OH group a much better leaving group, a sulfonate ester like tosylate or mesylate. Then, instead of acid, you use a base. The base doesn't protonate anything, it just promotes the departure of the good sulfonate leaving group, ensuring ionization happens only at that specific position. This gives much greater control. This approach is particularly valuable in synthesizing complex ring systems, like in terpene chemistry, often showing highly stereospecific migrations where the migrating group is anti to the leaving group.
Anti, meaning on the opposite side.
Yes, opposite side. In cyclic systems, this stereoelectronic control is crucial. The structure's rigidity often forces only one group to be properly aligned antiparaplanar to the leaving group, and that's the one that migrates. This dictates the rearrangement course in fused ring systems, for example.
And you mentioned earlier, pinacol rearrangements generally happen with retention of configuration at the migrating group's original position.
At the migration terminus, yes. The carbon the group migrates to, but the configuration of the migrating group itself is retained. This predictability is a huge plus for synthesis.
Okay, but then you mentioned Lewis acids can give inversion. How does that work?
Right, Lewis acids can also mediate rearrangements of these diomonosulfonates. And interestingly, they often lead to inversion of configuration at the migration terminus. This suggests a more concerted mechanism where the migration happens as the leaving group departs, possibly through a cyclic transition state involving the Lewis acid. Triethylaluminum, for example, is very effective and highly stereospecific. The reactants for these Lewis acid versions are often made using clever chelation-controlled additions, allowing access to highly enantiomerically pure starting materials, which then rearrange with high fidelity. This chemistry has even been applied to stereospecific ring expansions, combining epoxide chemistry with Lewis acid rearrangement to make complex cyclic structures that would be tough otherwise.
And you mentioned these pinacol reactions can be combined with other reactions, like the carbonyl N.
Yes, this is where synthetic strategy gets really elegant. Overman and coworkers developed powerful tandem protocols.
Tandem meaning one reaction flows directly into the next.
Exactly. You set up a carbonyl N reaction to form a ring and generate an intermediate which immediately undergoes a pinacol rearrangement, often leading to ring expansion.
So ring closure and ring expansion in one pot. Molecular remodeling.
That's a great way to put it. This sequence works for making oxygen heterocycles, like tetrahydrofurans, and also for carbocyclic compounds. We see examples forming functionalized tetrahydrofurans, or complex carbocyclic skeletons, using this tandem approach.
What about rearrangements involving diazonium ions? That sounds different.
It is, but it leads to similar intermediates. Aminomethyl carbonyls alcohols with an NH2 group on the next carbon react with nitrous acid, HONO, to yield ketones. The nitrous acid converts the amino group into a diazonium ion, Nationus N2+, which is an exceptionally good leaving group. It leaves a stable nitrogen gas. This loss of N2 generates the same type of beta-hydroxycarbocation intermediate we saw in the pinacol rearrangement. So again, a group migrates, assisted by the OH group, forming a ketone.
So different starting materials, same intermediate type, similar outcome.
Precisely. And when this is used to expand rings, it's specifically called the Tikhonov-Dimjanov reaction. A classic example is converting a cyclohexyl derivative into cycloheptanone, a 7-membered ring. Very useful for one-carbon ring expansions.
Is there another way to do ring expansions like this?
Yes, reacting ketones with diazomethane, CH2N2, can also lead to ring expansion. Diazomethane adds to the ketone carbonyl, then loses N2, and a group migrates to expand the ring. The intermediate is essentially the same carbocation as in the Tikhonov-Dimjanov.
But you warned earlier, the product is also a ketone.
Right, so the product ketone can react further with diazomethane, leading to uncontrolled expansion. That's why this method works best when the starting ketone is significantly more reactive than the product, often the case with strained cyclic ketones.
Got it. Strain makes the starting material react faster.
Exactly. Alcoholic solvents can help, and certain metal catalysts too. There are also related reactions using diazo esters with Lewis acids, again involving addition, N2 loss, and migration. These diazonium ion rearrangements have been used in complex synthesis, for instance, to precisely assemble 4 contiguous stereocenters in prostaglandins, or as part of sequences to build natural products like cedrine, demonstrating really fine control.
Okay, now you mentioned some related rearrangements that don't involve carbocations, even though they look similar.
Yes, this is an important distinction. The next two, the Favorsky and Ramberg-Backlund rearrangements, achieve similar structural changes but follow different mechanistic pathways, often involving cyclic intermediates but not carbocations.
First, the Favorsky rearrangement. What's that?
This happens when you treat alpha haloketones, ketones with a halogen on the carbon next to the carbonyl with a base. Alkoxide bases are common, leading to esters of products.
And like the Tiffano-Demjanov, it can change ring size.
Yes, if the starting ketone is cyclic, the Favorsky rearrangement results in a ring contraction. A classic example is turning alpha-chlorocyclohexanone, 6-membered ring, into a methylcyclopentanoate carboxylate, 5-membered ring ester. Powerful for shrinking rings.
What's the mechanism if not a carbocation?
It's fascinating and was debated for a long time. Strong evidence points to the involvement of a cyclopropanone intermediate.
A 3-membered ring with a ketone in it. Sounds strange.
Highly strained, yes. The base pulls off a proton alpha to the ketone, but on the other side from the halogen. This forms an enolate, which then attacks the carbon bearing the halogen, kicking it out and forming the cyclopropanone ring. The base, like alkoxide, then attacks the cyclopropanone carbonyl, opening the strained ring to give the ester product.
But you mentioned an alternative.
Yes, there's the semi-benzylic rearrangement mechanism, which can operate even if there's no proton to remove on that other alpha carbon. In this case, the base attacks the carbonyl first, forming a tetrahedral intermediate. Then the carbon skeleton rearranges as the halide leaves.
So 2 possible paths.
Yes, and the net structural change is the same. The energy balance might be quite fine. But key evidence, like different starting isomers giving the same product and isotopic labeling studies, strongly supports the symmetrical cyclopropanone intermediate in many cases. Crucially, how the cyclopropanone ring opens determines the final product structure. It opens to form the more stable of the 2 possible ester enolates, often influenced by substituents like phenyl groups. This reaction isn't just academic. It was a key step in synthesizing the natural painkiller epibetadine.
Okay, and the other non-carbocation one was the Ramberg-Backlund reaction.
That's right. This one involves alpha-halosulfones. Sulfones are sulfur atoms double bonded to 2 oxygens and single bonded to 2 carbons. Here, the halogen is on a carbon adjacent to the sulfone group.
So similar starting point setup, but with a sulfone instead of a ketone.
Exactly. The mechanism starts with a base removing the proton alpha to the sulfone, forming a carbanion. This carbanion then attacks the carbon, bearing the halogen intramolecularly, kicking out the halide and forming a 3-membered ring containing sulfur dioxide and unstable thyrane dioxide. This thyrane dioxide rapidly decomposes, eliminating sulfur dioxide gas, SO2, which is very stable, driving the reaction. This elimination is a concerted cycloelimination.
And the result? What's formed?
A carbon-carbon double bond. The overall transformation converts the carbon-sulfur bonds of the sulfone into a new C-C double bond where the sulfone used to be.
Wow, that's a neat trick for making alkenes.
It is. The modern method usually involves making the sulfone first, then halogenating it under basic conditions. It's been used to make complex polyenes. Because the SO2 elimination is concerted, it's very versatile. It works for making small rings, large rings, even highly strained bicyclic alkenes that are hard to make otherwise.
Any modern uses.
Absolutely. A really neat application is in making C-glycosides, which are important sugar derivatives. You can use a Ramberg-Backlund sequence to form an exocyclic vinyl ether from a thioether precursor, which can then be converted to the C-nucleoside. It's been used in synthetic routes towards molecules like ultramycin and artemisinin analogs.
Okay, one more category under carbocations. Fragmentation reactions. Breaking bonds instead of making them.
Sometimes, yes. Fragmentation just means a reaction where a carbon bond breaks. A specific type that occurs readily is the Grob fragmentation. This happens when you have a system set up so that a carbon atom beta, 2 bonds away to a developing electron deficiency, like a leaving group departing, can stabilize a positive charge. It works especially well if the atom gamma, 3 bonds away, is a heteroatom, like nitrogen or oxygen, with a lone pair. That lone pair can help push the reaction electronically, stabilizing the fragments.
Can you sketch that out, like ABCX, where X leaves?
Sort of. Think XCCYAB, where X is a leaving group. As X leaves, the CC bond breaks, the YA bond breaks, and you form CY, often involving the lone pair from Y, AB, like an alkene, and X. The molecule essentially breaks into three pieces, driven by the formation of stable products and the relief of strain, often.
Okay, breaking apart in a controlled way.
Exactly. It could be concerted or stepwise. The concerted version needs specific geometry and antiparaplanar alignment of the breaking bonds, allowing smooth orbital overlap. We see this in action comparing the reaction rates of similar molecules. One that can fragment is much faster because the fragmentation pathway is available. Useful starting materials are often 1-hetos-3-diols or beta-hydroxy ethers. Convert one OH to a good leaving group like a toslate, and the remaining oxygen promotes the fragmentation.
And the main use is
Often constructing medium-sized rings, like 7-10 members, by breaking a specific bond within a more accessible fused ring system, like fused 6- and 5-membered rings. Since it's often concerted, the stereochemistry is predictable. It's been used, for instance, to make key ring structures found in complex natural products like taxanes.
Are there other types of fragmentation?
Yes, beta-hydroxyketones can fragment, often promoted by Lewis acids. Organoboranes also fragment if there's a leaving group gamma to the boron. The intermediate is a tetrahedral borate formed by base addition. Stereochemistry is key. That antiparaplanar relationship is crucial for efficient fragmentation, especially from cyclic precursors leading to acyclic products. The geometry of the new double bond formed is often controlled, typically forming the E isomer. Fragmentation can be a great way to set stereochemistry into cyclic chains, starting from well-defined cyclic compounds. Examples include making complex spirocycles or strained bridgehead alkenes, like fragments of Taxol.
Right, that covers a lot on carbetations. Let's switch gears now to the other major player we mentioned, carbenes. Remind us what these are again.
Right, carbenes. Fundamentally, they are neutral, divalent derivatives of carbon. That means the carbon atom is only bonded to two other atoms and has two non-bonding electrons left over. What's crucial is their electron-deficient nature. Most carbenes have only 6 valence electrons around that carbon, making them highly reactive, electron-seeking species.
And you mentioned singlet versus triplet states.
Yes, this is a key aspect. Depending on how they're generated, a carbene can be formed in either a singlet or a triplet electronic state. These states have different electron configurations, geometries, and importantly, different reactivities. In a singlet carbene, conceptually, the two non-bonding electrons are paired up in one orbital, leaving another orbital completely empty. This makes it act like an electroprophile with a vacant site. In a triplet carbene, those two non-bonding electrons are unpaired, each residing in a separate orbital with the same spin. This makes it behave more like a diradical species with two unpaired electrons.
And one is usually more stable.
For simple carbenes like methylene, CH2, the triplet state is usually the ground state, lower in energy by about 8 kilocold more. Alkyl groups don't change this much. However, substituents that can donate electron pairs like halogens, FCl, oxygen, OR, or nitrogen, NR2, preferentially stabilize the singlet state. They can delocalize a lone pair into the carbene's empty orbital, reducing its electron deficiency.
So the substituents dictate the preferred state and reactivity?
To a large extent, yes. There are also more complex carbenes where pi delocalization plays a role, like in aromatic systems, which can also favor the singlet state. And we should also quickly define carbenoids and metallocarbenes. A carbenoid acts like a carbene but isn't truly free. It's still partially bound to something else, often a metal from its generation, like in alpha elimination reactions. Metallocarbenes, or metal-bound carbenes, are key intermediates in transition metal-catalyzed reactions. Their reactivity depends heavily on the metal and its ligands, how much electron density is transferred between the metal and the carbene-carbon. This can tune the carbene from highly electrophilic to much less so.
Okay, so these reactive carbenes, what do they primarily do in reactions?
The two main reaction types we'll focus on are addition to double bonds, forming 3-membered cyclopropane rings, and insertion into CH bonds, literally wedging the carbene-carbon between a carbon and a hydrogen.
Like molecular staples and wedges.
That's a good analogy. For truly free carbenes, these reactions happen incredibly fast, with very low activation energies. But this high reactivity means intermolecular reactions are often non-selective. They'll attack almost any CH bond nearby. However, intramolecular reactions within the same molecule are often controlled simply by proximity. The carbene reacts with the nearest CH bond, allowing for selective transformations and the formation of strained rings. They can also undergo rearrangements.
Let's dig into that reactivity, starting with cyclopropanation adding to alkenes. You mentioned the single-triplet difference is key here.
Absolutely crucial. A triplet carbene, being a diradical, adds to an alkene to form a 133 diradical intermediate. Before this can close to a cyclopropane, the electron spins need to flip, spin inversion, which is relatively slow. During that time, rotation can occur around the single bonds in the intermediate. The result: triplet carbene additions are non-stereospecific. You get a mixture of cis and trans-cyclopropane products regardless of whether you started with a cis or trans alkene.
Okay, so triplets scramble the stereochemistry. What about singlets?
Singlet carbenes are different. With their empty orbital, they act as electrophiles and can add to the alkene in a single concerted step. No diradical intermediate, no slow spin inversion needed. The consequence is that singlet carbene additions are highly stereospecific. The stereochemistry of the starting alkene is perfectly retained in the cyclopropane product. Cis-alkene gives cis-cyclopropane, trans gives trans.
That's a huge difference and a key diagnostic tool, you said. If you see stereospecific addition, it points to a singlet carbene. If it's non-stereospecific, likely a triplet.
Exactly. It's one of the classic ways to probe carbene mechanisms. This difference also shows up in reactivity patterns. Singlet carbenes, especially halo-substituted ones like CBr2, behave like other electrophiles, like Br2 addition or epoxidation, reacting faster with electron-rich alkenes. Triplet carbenes behave more like radicals. And as we noted, substituents strongly affect reactivity. Electron-donating groups like methoxy make the carbene less electrophilic, more nucleophilic, or amphiphilic. We can classify carbenes based on this behavior. Computational studies confirm these trends, relating reactivity to charge transfer and homo-LUMO interactions.
Okay, so how do chemists actually make these carbenes in the lab when they need them?
There are several standard methods, each with pros and cons.
Like diazo compounds. N2 seems like a good leaving group.
It's an excellent leaving group. Decomposition of diazo compounds, like diazomethane, CH2N2, is a very general method. It works for simple diazoalkanes, aryl-substituted ones, acyl-substituted ones. The main limitations are the synthesis and stability of the diazo compounds themselves. Small ones like diazomethane are toxic and potentially explosive, so they're usually made fresh and used immediately in situ.
How are they made?
Common routes include base-catalyzed decomposition of N-nitroso derivatives of amides or ureas. That's how diazomethane is often prepared. Another way is oxidizing hydrozones, especially for aryl-substituted diazo compounds. Alpha-diazoketones are particularly important synthetically. They can be made by reacting acyl chlorides with diazomethane, using a base to trap the HCl byproduct, or via diazo transfer reactions using sulfonyl azides, especially for cyclic ketones. Safety is a concern with azides, but safer polymer-bound versions exist. The driving force, as you said, is forming stable N2 gas. This decomposition can be triggered by heat, thermally, or light photochemically.
And the light method offers control over singlet versus triplet.
Often, yes. Direct photolysis tends to give the singlet initially, while using a photosensitizer promotes formation of the triplet state. Another crucial way to decompose diazo compounds is using transition metals, especially copper and rhodium compounds. This doesn't usually form free carbenes, but rather metal-bound carbenoids, which then do the chemistry. This is hugely important synthetically.
What about from sulfony hydrozones? You mentioned that was related.
It is. You take a ketone or aldehyde, make it an R-sulfony hydrazone derivative, and then treat that with base. This decomposes, likely forming a diazo compound as an intermediate, which then immediately loses N2 to form the carbene, or carbenoid carbitation, depending on conditions. Solvent choice is critical here. Provionic solvents often lead to carbocation chemistry, while probotic solvents favor the carbene pathway for additions or insertions.
And diazarenes, the cyclic isomers.
Yes. Diazarenes are three-membered rings containing two nitrogen atoms. They're cyclic isomers of diazo compounds. They readily lose N2 upon photochemical excitation, driven by ring strain and N2 stability. Historically, they were used more for mechanistic studies because they decompose cleanly. They're generally harder to make than diazo compounds, but useful routes exist, especially starting from carbohydrates or amino esters.
What about alpha elimination from halides, like making dichlorocarbene from chloroform?
There's a classic method, yes. Alpha elimination means removing a hydrogen and a halogen from the same carbon atom. It requires a strong base. The big limitation is that the starting material must not have any beta hydrogens on the next carbon over. If it does, you get beta elimination, dehydrophalogenation, to form an alkene instead, which is usually much faster. Chloroform, HCl3, is the perfect example. Strong base pulls off the proton, giving the CCl3 anion, which quickly loses Cl to give dichlorocarbene, CCl2.
And techniques like phase transfer catalysis help this.
Greatly. Using phase transfer catalyst allows the base, like hydroxide and water, to interact effectively with the chloroform in an organic solvent, making the reaction much more practical for cyclopropanating alkenes. Sonication with powdered KOH also works. You can also get alpha elimination using strong organometallic bases like alkylithiums on things like dichloromethane or benzyl chlorides. The intermediates here might be carbenoid's alpha-halocylithium species rather than free carbenes, but often they react as if the free carbene is present. This method is mostly limited to polyhalogenated compounds because the halogens are needed to stabilize the intermediate anion.
Lastly, organomercury compounds. You said they were more stable.
Generally, yes. The carbon-mercury bond is more covalent than carbon-lithium. Compounds like phenyl trichloromethylmercury, PHHGCCl3, can often be isolated and stored. They decompose upon heating to generate the carbene, like CCl2, via an alpha elimination mechanism. The decomposition is usually the slow step. They're useful precursors, especially for halogenated carbenes, but require heating, sometimes to 80 degrees C or more, though some iodide versions are more reactive.
Okay, we know how to make them. Let's get back to their main reaction. Cyclopropanation. You stress the stereospecificity difference.
Right. Singlet carbenes give stereospecific addition, alkene geometry retained. Triplet carbenes give non-stereospecific addition, mixtures result. This addition is highly exothermic, breaking one pi bond, making two strong sigma bonds, and very fast. It's a cornerstone method for making cyclopropane rings.
And the Simmons-Smith reaction is a classic way to add just CH2.
One of the best, using diadomethane, CH2I2, and a zinc-copper couple. The active species is thought to be iodomethyl zinc iodide, ICH2SNI. It's a carbenoid reaction, not free, CH2.
It's stereospecific.
Completely stereospecific. And crucially, it doesn't involve the hazardous diazomethane. Modifications use dibromomethane or diethyl zinc with haloalkanes. Lewis acids can accelerate it, and zinc purity matters. Computational studies shed light on the mechanism involving the zinc species. Variations use zinc reagents with oxyanion ligands like trifluoroacetate or phenoxide, which can be very effective for less reactive alkenes.
And the hydroxy-directing effect, that seemed really important.
Hugely important synthetically. If you have an allylic or homoallylical alcohol, the CH2 group is delivered syn to the same face as the OH group.
Why, again, complexation.
Yes, the thinking is the zinc reagent coordinates to the Lewis basic oxygen of the hydroxyl group, and that directs the delivery of the CH2 unit to that face. It's not just hydrogen bonding. Lithium salts work even better. This allows for fantastic diastereoselectivity.
Can you make it enantioselective?
Yes, by using chiral auxiliaries or chiral catalysts. A notable example uses a chiral dioxyborylane ligand derived from tartaric acid with diethyl zinc diadomethane. This can give 90% E and has been used iteratively to build complex natural products with multiple cyclopropane rings.
What about the metal-catalyzed versions using diazo compounds, copper and rhodium?
Also extremely important. Copper salts, like QI or Q2 triflate, or copper complexes, like silane complexes, are classic catalysts for decomposing diazo compounds, like ethyl diazoacetate, to form substituted cyclopropanes via copper carbenoid intermediates. Rhodium complexes are perhaps even more versatile now. The workhorse is rhodium acetate dimer, RH2OAC4, but many others with different carboxylate or amide ligands exist. These rhodium catalysts generate rhodium carbenoid intermediates. The ligands on the rhodium are crucial because they tune the electrophilicity of the carbenoid.
How does that help?
It allows for amazing control over selectivity. For example, a highly electron-withdrawing ligand like nonafluorobutanoate makes the carbenoid very electrophilic, perhaps favoring CH insertion or aromatic substitution. A less withdrawing ligand like caprolactamate makes it less electrophilic, favoring cyclopropanation. You can literally dial in the desired reaction pathway by choosing the right rhodium catalyst.
That's incredible fine-tuning.
It is. Extensive mechanistic work, including kinetics and computations, has mapped out the catalytic cycle. N2 loss is rate determining. The addition step is a direct carbene transfer from the rhodium. The models beautifully explain observed stereoselectivity based on minimizing steric clashes in the transition state between the substrate and the bulky catalyst ligands.
Any other ways to make cyclopropanes? You mentioned the mercury compounds and alpha elimination briefly.
Yes, the haloalkyl mercury compounds work by heating, useful for some functionalized cyclopropanes, and alpha elimination, especially making dichlorocyclopropane from chloroform under phase transfer conditions, is quite common.
Could you give a few examples from the literature to illustrate these?
Sure. Simmons-Smith is great for applying that hydroxy-directing effect in complex settings, like making intermediates for crenulite derivatives, showing high selectivity. Metal-catalyzed examples show copper or rhodium efficiently forming cyclopropanes, often with very low catalyst loadings for rhodium. Palladium acetate has even been used with diazomethane. Haloalkyl mercurials provide routes to functionalized rings, though needing heat. Alpha elimination examples show low-temperature generation from lithiated species or the standard phase transfer dichlorocarbene addition. And importantly, intramolecular cyclopropanations, often metal-catalyzed, are key for making strained bicyclic or polycyclic systems, sometimes involving fascinating subsequent rearrangements like divinyl cyclopropane shifts.
And the enantioselective versions, making just one mirror image.
Yes, a major area. Both copper and rhodium catalysts have been developed with chiral ligands. For copper, ligands based on chiral bis-oxazolines, BOX, or related imines, are very effective. For rhodium, chiral ligands derived from amino acids, like pyroglutamate, often incorporated into the bridging carboxylate or carboxamidase structures, are extremely powerful. Catalysts like those developed by Davies, chiral pyrrolidinones, PY, and Doyle, chiral imidazolidinones, IM, give outstanding results.
How do they control the chirality?
The chiral ligands create a specific 3D pocket around the metal-bound carbene. They essentially block off one direction of approach for the alkene, forcing it to come in from the other side, leading to high enantioselectivity. Computational models help visualize how bulky groups on the ligand steer the substrate. Both copper and rhodium systems can give excellent EES, often well above 90–95%, enabling the synthesis of complex chiral molecules.
Okay, besides addition, the other main carbene reaction was insertion, wedging into CH bonds.
That's right. Carbene interposes itself to an existing bond, usually CH.
Mechanism, singlet versus triplet again.
Yes. Singlet carbenes can insert in a single step, with complete retention of configuration at the carbon being inserted into. That's the key diagnostic. Triplet carbenes react via a two-step process. Hydrogen and atom abstraction to form a radical pair, followed by recombination. The stereochemical outcome depends on how fast that radical pair recombines versus how fast stereochemistry scrambles at the radical centers. Retention is the hallmark of the concerted singlet pathway.
But you said intermolecular insertion is messy, not selective.
Generally, yes. Free carbenes are so reactive they'll insert into almost any CH bond available, leading to statistical mixtures. Even with some directing effects from substituents, the selectivity is usually too low for practical intermolecular synthesis.
But intramolecular is useful.
Much more useful. Because the carbene is tethered, it preferentially inserts into the CH bond that's closest in space, often dictated by forming a 5-membered ring transition state. This proximity control gives good yields and selectivity. It's a fantastic way to make strained rings or access specific positions within a molecule.
And rhodium catalysts are good here too.
Excellent. Rhodium carboxylates, or carboxamidates, are very effective for intramolecular CH insertion of alpha diazo ketones or esters. There's a strong preference for forming 5-membered rings. Insertion into tertiary CH methane is preferred over secondary CH methylene. Again, catalyst choice is huge. You can tune the selectivity between insertion and cyclopropanation, or between different CH bonds by changing the rhodium ligands. More electrophilic catalysts favor insertion. Chiral rhodium catalysts can achieve high enantioselectivity in these insertions as well. Sterically-bulky catalysts can also enhance selectivity for specific CH bonds. The 5-membered ring preference is very strong. Studies show that even as you lengthen the chain connecting the diazo group and potential insertion sites, only 5-membered ring products, lactones or ketones, are formed efficiently.
What about forming lydes? You mentioned that briefly.
Yes, if there's a nucleophilic atom with a lone pair, like oxygen in a carbonyl or ether or sulfur or nitrogen near the carbenoid carbon, they can react to form an Y-lide. And limlite is a neutral species with adjacent formal positive and negative charges. Carbonylides, for example, can form from alpha-diazo ketones reacting with a catalyst. These phthalines are 1003 dipoles and can undergo cyclolytion reactions, either intra- or intermolecularly, forming new rings. Oxonium phthalines form when carbenoids react with ethers or acetyls. These are particularly interesting because they readily undergo 2-methyl-3 sigmatropic rearrangements, a type of concerted bond reorganization leading to complex structural changes.
And rearrangements, so what do carbenes themselves do?
The most common rearrangement for simple alkyl carbenes is a 1-value-2 hydrogen shift. A hydrogen from the adjacent carbon moves over to the carbene carbon, forming an alkene. This is often very fast and competes with insertion or addition reactions. Alkyl or aryl groups can also migrate, a Dwyer-Yukawa shift, to stabilize the carbene center, forming a different alkene. Sometimes multiple pathways compete. Rearrangements can lead to unusual structures like highly strained bridgehead alkenes, vinyl carbenes, carbene next to a double bond, typically cyclized to form cyclopropenes. And cyclopropylidenes, carbene-carbon, is part of a three-membered ring, almost always ring open to form alkenes.
Finally, you mentioned the Wolff rearrangement is related, but not a carbene reaction.
Explicitly, yes. It's conceptually related, but mechanistically distinct in many cases. The Wolff rearrangement is the thermal or photochemical decomposition of an alpha-diazo ketone, which rearranges to form a ketene, R2CCl.
So diazo ketone to ketene. Is a carbene involved or not?
The evidence suggests that in photochemical reactions, a carbene intermediate is often formed, which then rearranges. However, under thermal conditions, the reaction can often proceed via a concerted mechanism. The nitrogen leaves at the same time as the R group migrates, directly forming the ketene without ever forming a discrete carbene intermediate. It bypasses the carbene.
Wow. Okay, so what does this all mean? We've covered a lot of ground today, from the fleeting dance of carbocations used for CC bonds and clever rearrangements like the pinnacle to the intricate ballet of carbenes, doing additions, insertions, and their own rearrangements. We've seen how these super high-energy intermediates, even though they only exist for tiny moments, are absolute cornerstones for building complex molecules.
Exactly. The practical synthetic applications are immense. Building complex rings, like those in steroids or terpenes, creating molecules with very specific 3D shapes, stereochemistry, even mimicking the way nature puts together things like lanosterol. The depth of understanding we now have about their reactivity, their selectivity, it lets chemists design these incredibly precise molecular transformations. It's not just theory. It's about making molecular architecture actually possible, building things atom by atom.
It really is amazing control. So, given how much control chemists now have over these highly reactive, almost chaotic-seeming intermediates, what other impossible molecular structures do you think we might learn to build with such precision in the coming years? What new functions could they unlock? It's definitely something to think about. We invite you, our listener, to maybe explore further into some of these reaction types, polyene cyclizations and regioselective catalysis, or look into the modern synthetic challenges where these intermediates are making a difference. Thank you so much for joining us on this deep dive. We really hope this exploration into the world of reactive intermediates has given you a powerful new shortcut to being well informed.
Until next time, keep digging deeper.